Chapter 9, Section 1 is all about simplifying and evaluating nth roots using radical notation. We will begin with square roots. A number a is a square root of a number b if a squared is equal to b. For example, 2 squared is equal to 4, and negative 2 squared is equal to 4. Both 2 and negative 2 are square roots of 4. For a positive number b, the principal square root of b, written like this, is the positive number a such that a squared is b. So the principal square root of 4 is positive 2. Even though negative 2 is a square root of 4, it is not the principal square root. Positive 2 is. Let's take a look at a few examples. We start with the square root of 81. Recall that 9 squared is equal to 81. So that means the principal square root of 81 is equal to positive 9. Now let's look at the square root of 9 over 49. Consider that 3 over 7 squared is equal to 9 over 49. So the square root of 9 over 49 is equal to 3 over 7. Finally, let's look at negative square root of 225. 15 squared is equal to 225. So that means the square root of 225 is equal to positive 15. And the opposite of the square root of 225 is the opposite of 15, or negative 15. If you have a real number a and you have the square root of a squared, this is simply equal to the absolute value of a. Suppose we have the square root of 2 squared. That's equal to the square root of 4, or simply 2. So the square root of 2 squared is 2. But also consider that the square root of negative 2 squared is also equal to the square root of 4. And the square root of 4 is equal to positive 2. So the square root of negative 2 squared is positive 2, or the absolute value of negative 2. Let's take a look at example 2. First, we have the square root of x to the 14th. Consider that we could rewrite x to the 14th as x to the 7th squared. Now we have the square root of x to the 7th squared. So this is equal to the absolute value of x to the 7th. Now consider the square root of 64x to the 24th. We could rewrite this as the square root of 8x to the 12th squared. So we have the square root of 8x to the 12th squared. This is equal to the absolute value of 8x to the 12th. 8 is already a positive number. And since 12 is an even number, x to the 12th is also positive. So this is simply equal to 8x to the 12th. From this point on, we're going to assume that all variable factors that are in a radicand represent non-negative real numbers. That way we don't need to use the absolute value bars when we are simplifying radical expressions whose radicands contain variables. Let's extend this idea of a square root to an nth root. For any positive integer n greater than 1 and any number b, if a raised to the exponent of n equals b, and both a and b have the same sign, that is, they're both positive or both negative, then a is the principal nth root of b. And we write that this way. The number n is called the index of the radical. Let's take a look at example 3. Notice that in the first one, the index is a 3. And just like when the index is a 2 and we call that a square root, when the index is a 3, we also have a special name. We say that this is the cube root. Consider that 10 cubed is equal to 1,000. So we could rewrite this as the cube root of 10 cubed. And with an exponent of 3 and a cube root being opposites, this simplifies to positive 10. Now let's look at the cube root of negative 343. Consider that negative 7 cubed is equal to negative 343. So we could rewrite this as the cube root of negative 7 cubed, which is simply negative 7. When the index n is odd, like these cube roots, the principal nth root, like our 10 and negative 7, has the same sign as the radicand, like the positive 1,000 and negative 343. Now let's look at the fifth root of 32 times a to the 40th times b to the 65th times c to the 15th. Let's see if we can write what's inside as something raised to the fifth power. Consider that 32 is equal to 2 to the fifth, and a to the 40th, we could write that as a to the 8th to the fifth. We could also write b to the 65th as b to the 13th to the fifth, and c to the 15th, that can be written as c cubed to the fifth. So now we have the fifth root of 2a to the 8th, b to the 13th, c cubed to the fifth. So this is equal to 2a to the 8th, b to the 13th, c cubed. Let's take a look at another example. This time, we have the square root of a polynomial. We would really like to write the radicand as something squared. Let's take a closer look at this polynomial. X squared plus 10x plus 25. This polynomial can be factored as x plus 5 times x plus 5. And that can be rewritten as x plus 5 squared. So we have the square root of x plus 5 squared, which is simply x plus 5. Let's take a look at the product rule for radicals. For any root n, if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is equal to the nth root of a times b. As long as the indices match, that is, we have the same n, we can multiply the two radicands together. Let's take a look at example 5. We start with 9 root 12 times 8 root 3. Let's write this a little differently. This is the same as 9 times 8 times root 12 times root 3. 9 times 8 is 72. And since both of these are square roots multiplied together, we can combine them and write the square root of 12 times 3. And since 12 times 3 is 36, this becomes 72 root 36. The square root of 36 is 6. So we have 72 times 6, or 432. Let's take a look at the next one. We have the square root of 6b to the 5th times the square root of 150b cubed. Since these are both square roots, we can combine them into a single square root and multiply what's on the inside. So we have the square root of the product of 6b to the 5th and 150b cubed. Simplifying, we have 6 times 150, or 900, and b to the 5th times b cubed, which is b to the 8th. 900 can be written as 30 squared, and b to the 8th could be written as b to the 4th squared. So this simplifies to simply 30b to the 4th. Now let's look at the quotient rule. The quotient rule tells us that we can divide just as simply as we multiplied. The nth root of a divided by the nth root of b can be rewritten as the nth root of a divided by b. Let's take a look at example 6. Notice that we have a fourth root in the numerator and a matching fourth root in the denominator. So we can rewrite this as a single fourth root with the quotient of 405 times p to the 29th over 5p to the 5th. Now we can simplify the quotient on the inside. 5 goes into 405 81 times, and p to the 29th divided by p to the 5th simplifies to become p to the 24th. So we have the fourth root of 81 p to the 24th. Now let's see if we can write 81 times p to the 24th as something raised to the 4th power. 81 is equal to 3 to the 4th, and we could rewrite p to the 24th as p to the 6th to the 4th. So this simplifies to 3 times p to the 6th. Now let's take a look at a radical function. In example 7, we need to evaluate the radical function f of x when x is equal to 20. That is, we need to find f of 20. In order to find f of 20, we need to substitute a 20 for the x inside the square root. So we have the square root of 3 times 20 plus 4, then minus 17. Simplifying, we have the square root of 3 times 20, or 60 plus 4, minus 17. or the square root of 64 minus 17. And since the square root of 64 is 8, this simplifies to negative 9. So f of 20 is equal to negative 9. I quickly mentioned how a square root cannot have a negative inside, but that a cube root can. This has to do with the domain of radical functions. To find the domain of a radical function involving an even root, we need to find the values of the variable that make the radicand non-negative. We cannot have negatives inside of a radical function that has an even root. However, the domain of a radical function involving odd roots is the set of all real numbers. Let's take a look at example 8. In example 8, we're going to find the domain of each radical function and write it in interval notation. Beginning with f of x equals the square root of 2x minus 9 plus 23, we have a square root. Even though it's not written, the root here is a 2, which is an even number. That means that this radicand cannot be negative. It must be non-negative. We can only evaluate this function for values of x that cause 2x minus 9 to be greater than or equal to 0. Let's solve this inequality for x. Adding 9 to both sides, we have 2x is greater than or equal to 9. And dividing both sides by 2, we have x is greater than or equal to 9 over 2. So x values that are greater than or equal to 9 over 2 will cause the radicand to be non-negative. So we know that the domain of this function is all values from 9/2 to infinity. Now let's look at this second function. F of x is equal to the 7th root of 9x plus 13 plus 20. This time our n is 7. That is, we have an odd root. Odd roots can have positives, negatives, or 0 as the radicand. So the domain of this function is simply all real numbers. In interval notation, we write this as negative infinity to positive infinity. And that concludes this lecture video on nth roots written in radical notation.